talk about the gravitational action. So I know you've already seen this with David in the first GR course. So what we're going to do today is to kind of refresh our memories, perhaps fill in some of the things that David promised I would talk about, and discuss what happens to this boundary term when you do the Euler-Lagrange variation. So just very somewhat more quickly, we'll review some of the things that you've already covered. So when we are doing, the whole point about Euler-Lagrange is that you have some sort of action which depends on a field, and gravity is a little bit different because our field is the metric, that's kind of our physical quantity, and our gravitational action is unusually written in terms of second derivatives of the metric rather than like a canonical kinetic term, dg squared. And in part this is sort of due to the issues we have with differentiation on manifolds. So in here we know that the geometry R depends on G, and clearly our volume factor, our volume element, root G, also depends on the metric. So I'm going to vary things with respect to the inverse metric. Which I'm not entirely sure if David did it that way around or not, but essentially it's a minus sign. So delta G upstairs is more or less minus delta G downstairs. So first of all, if we look at our determinant, we use the identity det is x of trace of log of a matrix. So that's how we find the variation. So delta of det G is therefore det G, coming from the exponential, and then it's trace of G inverse delta G, which we replace by minus trace of G delta G inverse. So that's how we take our variation of square root G. I'm being a little lax here about minus signs, so you just understand it's, it's the modulus of det G. Then, for varying R, that is what R is, just the trace of the Ricci tensor. So delta R has two pieces, the first of which is already packaged nicely for us because it's the Ricci tensor contracted with the variation of the inverse metric. But the other piece is a piece which I think David promised was a total derivative, and it's the variation of Ricci. So if we take a coordinate basis, and write down what the components are, then we simply go through, vary everything inside that bracket. wrote all those pieces out for a reason, because I want to kind of pair things up. You sort of see that here, if I look at this term, for example, when you have, although the connection isn't a tensor, the difference in connections is a tensor. And so this thing here is a covector, one downstairs index. So we're taking the covariant, we're taking the partial derivative with respect to b, the b coordinate of the a component of that vector. And then you see here, that gives you this term and this term combine to give you the covariant derivative of delta gamma. And then here, what you're left with is, again, a tensor, but now this is a rank 1, 2 tensor. And down here, you find that, indeed, you are getting the 3 connection terms that turn that partial derivative to a covariant derivative. And so you find that the variation of the Ricci tensor is given as an expression in terms of covariant derivatives of the variation of the connection. So this is known as Palatini's lemma. And then finally, we want to get an expression for the variation of the connection. And to do this in a sort of fairly economical way, I'm going to choose a very specific set of coordinates. So these are called normal coordinates, NC, and they correspond to a local inertial frame. So remember when Einstein was thinking about sort of developing his general relativity, he was thinking a lot about the equivalence, or otherwise, of acceleration and gravity. And so he was sort of pondering what an inertial frame was and sort of thinking about sort of freely falling elevators and stuff. And so essentially that's what one of these frames is. It's a freely falling elevator. And what it means is that if you're in a completely inertial frame, you're in a locally Cartesian frame, and so you have no connection components. And so what's the difference between an accelerating frame and a gravitational frame? It is the fact that you've got tidal forces. And the tidal forces show up in Riemann curvature, which really shows up in that first line of that expression, which are the derivatives of the connection. So a local inertial frame is a choice of coordinates that sets gamma equals 0 to point, but not d gamma. And we can always do that. So in essence, what we're doing is we're saying the first derivative of the metric is 0 at the point. We're just sort of choosing our coordinates to do that. So that means that delta gamma ABC, which if we weren't sort of thinking too hard, we just sort of went through and said, what is delta gamma? We'd first of all vary the inverse metric in front of the derivatives of g. Then we'd vary g inside. So this first term is 0 because we're in normal coordinates. So it's just the second term that has a non-zero answer. But then in normal coordinates, our partial derivative is the same as the covariant derivative. So I can rewrite try and jump ahead. So in normal coordinates, I can replace those partial derivatives by covariant derivatives. But now this is a completely covariant geometric expression. It's true in the normal coordinate frame, but because it's true in one coordinate frame and it's a tensorial expression, it's therefore true in general. So that means if I want to write delta gamma in terms of my inverse g's, I simply basically put a minus sign. So I've put the G inverse there just to emphasize that it really is varying the inverse metric rather than varying G, because the indices are sort of going up and down like crazy. So now, having got delta gamma, I can go back to Palatini's lemma and find the variation of the Ricci tensor. So in terms of wanting to know what we do with varying our action, our Euler-Lagrange method, we simply contract that expression on A and B. So you see now that I've sort of arranged the terms so that when you take the trace of this, the first line, the first two terms give you the same thing, and the second two terms give you the same thing. Now I've got my indices happily upstairs on delta G. And of course, this is a total derivative. So because our Einstein action simply has root GR, this term doesn't contribute to the bulk. It just integrates up to give a boundary term. But if we had some modified gravity action, say with instead of root G, it was root G e to the phi or some other such thing, when we integrated by parts, we would get extra terms. So if you're modifying gravity, this expression becomes relevant. So let's now go back to our action. And we integrate up the variation of the Einstein-Hilbert action. So we've got the first piece. And the first piece was straightforward. It was that first term of delta R, so that was RAB, and it's the term from the variation of square root of G. So that gives us the Einstein tensor. So that's the bit that we want. That's the bit you've seen. And then we get a boundary term. And this is where we kind of feel a bit uneasy. Because our boundary term does not depend on delta G, it depends on the derivative of delta G. And the usual rules of the game of Euler-Lagrange are that you set the variation of your field to 0 on the boundary, not the derivative. So, although Einstein and Hilbert had derived the Einstein-Hilbert action, and it seemed like the right thing to do, there's this sort of slightly uncomfortable nature of what's happening on the boundary. But if you let the boundary go to infinity, I suppose, asymptotically flat spacetimes, blah, blah, you don't care. However, once people were coming back to these things in the sort of 60s and 70s, it became a bit more of an issue, because if you want to start sort of thinking about doing some sort of path integral for gravity, then you want to actually have the action for spacetimes to put in some sort of stationary phase types approximation. And if you just have the Einstein-Hilbert term, as I was saying the other day, there are a lot of physically distinct spacetimes that have 0 Einstein-Hilbert action. So the Kerr family of black holes would all have 0 action. Gravitational waves would have 0 action. So all sorts of interesting manifolds are completely indistinguishable from the perspective of the Einstein-Hilbert action. And the only clue that we have that there's something missing is this boundary term. So let's see, how do we deal with the boundary? So if we want to deal with the boundary, we're sort of imagining that we have, this is our manifold, then this is our boundary. So just crudely speaking, let's sort of think about what that is. So in the case of a boundary, the boundary has a dimension one lower than that of the manifold. And typically we might think of a boundary as, let's say, we're sort of inside some large region. Maybe our boundary might be at r equals constant, some large r. And an r equals constant surface, we can get to the metric of that by simply covering up the dr squared piece. So our boundary sort of appears to have a metric, and indeed we're kind of assuming it does, because we're sort of writing normals, we're writing root g's, and we're sort of thinking about covariant derivatives, etc. So we think, therefore, what we need to be able to do is to be able to think about submanifolds of a manifold, because that's what a boundary is. It's kind of a special one, but it's a special case of a general thing, which is a submanifold. And this is known as the Gauss-Codazzi formalism. So what we're going to do now is look at how we describe submanifolds in a bigger manifold. So let's set the stage. So I'm going to imagine I have a submanifold which I'm going to call sigma. So sigma lies within M. And I'm going to suppose it has some sort of dimension d. And I'm going to say the dimension, just for the, because I'm going to need to label it, the dimension of my manifold is capital D. And I'm going to say that that's equal to little d plus n. So my submanifold has dimension little d. So we've got d coordinates in here, and we have n normals. And I'm going to say that I've got coordinates on sigma and coordinates on M. So let me just define a couple of things. So it's sort of obvious if our manifold, submanifold's got dimension little d, and the dimension of the big manifold is capital D, which is d plus n, then the codimension of sigma, in other words, how many sort of dimensions does sigma not contain, is little n. And what it means is that we can place n linearly independent normal vectors. So you're thinking of a point on sigma, you're thinking of the tangent space at that point, P. You're imagining that you've got little d vectors that are also tangent to sigma, and then what remains are little n extra directions, which you can parameterize by these normal vectors, ni. So we have this notion that our ni's So what that actually means is if you've got a coordinate function on sigma, then the normal vectors annihilate that coordinate function. So that's kind of what we mean by normal to the surface. So from our sort of physicsy index point of view, we can also write this with our metric, etc., etc. So we have our local coordinate functions in the manifold M, which are the x mu's. We've got our coordinate basis in sigma, d by d sigma a, and that's kind of telling us that this quantity here kind of projects us down from the manifold M tangent space to the submanifold sigma. So I'm going to choose my normals to be unit normals, because I can always rescale them.
Sorry.
So,
the label A on Bill Sigma, is that like a coordinate label or?
Yeah. So, I mean, so what you should sort of think here, I mean, is again, it depends if you've read a bit about string theory, then you might sort of have an intuitive notion of this submanifold. But you're imagining that, so here we are in this room, we've got our x, y, z coordinates. And so our submanifold might be a piece of paper, okay? So our piece of paper has its own coordinate system, which is a different choice. Maybe we call it a different xi and an eta, or maybe I have a cylinder and I call it z and theta. It just depends, but this is a different coordinate system to what's sitting around in the room. And so these are, the reason I put a capital letter is to distinguish between, so here, I suppose, if I go back to thinking here, my mu is going 0, 1, 2, up to d, minus 1. Count. Whereas the A is going from 1 to little d, or 0, 1 to d minus 1, depending on the nature of the submanifold. So obviously if n is a time-like normal, then n squared is plus 1. And this, for example, would be if you were doing the ADM formalism for gravity. So this is where you're kind of thinking about gravity as being a sort of evolution of space-like slicings. So this sort of corresponds to GR as a dynamical theory. What I'm going to, just for the sake of keeping things as straightforward as possible, I'm going to assume that my normals are all space-like. So then n squared is minus 1, and this is sort of what we're doing, or what we imagine that we're doing from this Euler-Lagrange perspective, because usually you're thinking about sort of a region of your space-time and imagining a boundary, some sort of boundary that is defined by its spatial location. So this is what we'll do. So in other words, I'm going to say that Ni mu, Nj mu is minus delta Ij. So it just means I don't have to keep worrying about the signs associated to whether my normal is space-like or time-like. So, at the moment, all I've really said is, oh, we've got a manifold, it's got coordinates. Our manifold's got coordinates, it's got normals. The normals are defined as sort of, having zero dot product, if you like, with vectors parallel to the manifold. But now we want to go a bit further, because we don't just want sigma living in M and not caring at all about its sort of higher dimensional parent. We want to have this notion that sigma is part of M. It's just some restricted surface lying in M. In other words, the metric on sigma is inherited from the metric on the manifold M. So this is what we do first. So to get the induced metric on sigma, what we need to do is to project out all of the orthogonal degrees of freedom. And since we've kind of chosen our normal to be encoding those degrees of freedom, all we do is add NA and B to our manifold metric. So this is the metric that sigma inherits from M. So I could also, so notice this is in the tensor tangent bundle of M. But I could also think, well, hang on, sigma's a manifold in its own right, so can't I actually just express this metric in terms of the tangent space of sigma? So remember we talked about maps between manifolds and the push forward and the pull back. Here's an example of using this pullback where the dimensionality of the manifolds is different. So in this case, we can pull back from the higher dimensional to the lower dimensional manifold any covector indices. And intuitively, we just see, well, this is kind of doing the obvious thing. We have our G on the manifold, and we simply project it down using these dx by d sigma functions. So that's just sort of more or less stating the obvious in the sense of it saying we want our submanifold to inherit its structure from the parent manifold. This is what the metric is. But of course we know that we don't just have the metric, we have a connection on the higher dimensional manifold, and of course curvature. So what happens to the connection? So there's two ways, yeah?
Could I just ask, what's the relation between HAB and gamma AB?
They're basically containing the same physical information. H is an element of the tangent bundle of the parent manifold M. Gamma is an element of the tangent bundle of sigma.
So if you wrote the components of HAB in terms of the coordinates on sigma, would you get gamma AB?
Yeah, but the coordinates sigma are exclusive. The little sigma a's are coordinates on sigma. So I think what the way to say it is that you would coordinatize your space-time by using sigma as a base. So sigma has coordinates, let's say this piece of paper has coordinates x, y. I now want to extend that to the coordinates in the room. I'm going to add an extra direction z. So then, in that case, because I have chosen the coordinates to start with sigma and then I've just built up the perpendicular coordinates, it would be true that the elements of H would be the same as the elements of gamma. And everything else of H would be 0 because it doesn't have any components normal. But these sigma a's are exclusively living on sigma. So you would have to then say, well, my x's would correspond to, let's say, sigma a and yi, for example. Okay? They contain the same information, H and gamma, but they are in different spaces. Okay? So we define our extrinsic curvature, K, in general, as the symmetrized covariant derivative of the normal projected onto the sort of parallel part of the tangent space. So if I just kind of sketch, here is a submanifold of R squared. It's a line. The normal is this. And as I move along the line, my normal is changing. So here, as I sweep out across my curve, my normal is changing direction. And in this case, you sort of see, well, actually, the amount by which it's changing is actually parallel to the curve. I could also write this, again, if I wanted to, I could just project the indices down. That would just be another way of doing it, which gives me a slightly different way. Of representing the extrinsic curvature, which can be useful. And if I'm going to actually label this as a D. So essentially, to get the connection that sigma inherits, you just take a derivative in the higher, the parent manifold, the upper manifold, and project every index you can find down parallel to the manifold. So that's how you find this intrinsic connection. And so here, again, this expression is kind of something that, you know, you might again see if you're trying to think about these submanifolds as actual physical objects, again, such as, say, a string worldsheet. Then your sort of equations of motion for these x mu, the higher dimensional coordinates, or the coordinates in the higher dimensional manifold, sort of tend to satisfy a wave equation, which is the trace of the extrinsic curvature vanishing. So there's just one other thing that's part of this structure. In each case, I've drawn the normals in rather an intuitive way. So here, I've kind of drawn this, of course, in 2 dimensions, there's not much you can do, but this could be also a line in 3 dimensions with 2 normals. And here I've kind of drawn my normal in a very intuitive way, saying that, well, I've picked a normal where the line is curving and orthogonal, you know, nothing's happening orthogonal to that line. But if I have more than one codimension, like a line in 3 dimensions, surely if I have one normal basis, say, that does this, I could also be perverse and say, well, okay, I'm going to turn my normals around as I go along the line. And that's surely going to give me something slightly different in terms of how I split up the tangent spaces. And so this is what the normal fundamental form is telling you about. So we don't usually use it in GR, but it's kind of telling you about how twisted your submanifold is. So if you had a helix, for example, you'd sort of see a normal fundamental form coming in. So now we can decompose the curvature on sigma. So sigma, if you like, inherits curvature because M is curved, but also sigma might inherit curvature because it itself is curved. So the obvious example of that is the 2-sphere. The 2-sphere embedded in R cubed is curved. It's a constant curvature manifold. It has intrinsic curvature. R cubed has none. So in that case, the curvature of sigma is coming purely from the embedding of the surface in R cubed. So the first, in order to find the Riemann curvature of the submanifold sigma, we first take the Riemann curvature of the parent manifold and again project out all the indices like crazy. But then there's an extra piece which comes from the embedding. And so we then have our extrinsic curvature squared. So you could think of that as being kind of analogous to the gamma-gamma piece in the Riemann tensor. So there's, I guess, a handout deriving this on the wiki or something. So, you know, you basically prove it. So in other words, sort of grad A, grad B minus grad B, grad A. So you look at this, the definition of the Riemann tensor to actually derive this expression. So now, before it disappears, I want to come back to thinking about this boundary term. So I'm going to sort of restrict myself to submanifolds that are codimension 1 because they're like walls. It's like an edge to a space. It's also true that if you just have a single normal, then you don't have to worry about things like the normal fundamental form, and there's a lot of sort of extra bits and pieces that just disappear. If we have a single codimension, what it's like is having a wall. We've got a wall, and we can think of that as an edge to the space-time. So again, since I've only got one normal direction, I start off with a unit n, and I have a choice. How do I extend that into the bulk? That's kind of my decision what to do, because all we're interested in is the boundary. So I'm going to choose, I'm going to say, my normal, first of all, it's a unit normal, and I'm going to extend it into the bulk geodesically. So what this means is that if I go along the normal, it's the distance I've traveled along the normal is how far I am from the wall. So this is like taking, you know, from a point, dropping a normal to a surface. Okay? So this is my assumption, my supposition about the normal. It's unit, and it extends geodesically into the bulk. And of course, my first fundamental form is just G plus NN. So now, because I want to try to think about this extra piece, this boundary term in the action, I want to think about what happens if I just vary things a little bit. So I'm going to look at varying my metric. So even though I vary my metric, I still want the normal to kind of still be this Gaussian normal. So that means n squared should still be 1. So I vary the condition for the length of n being 1, and that gives me a relation between delta n projected along n, and the normal variation of g mu nu. I also need n to be a normal. So that means that n dotted with h has to remain 0. And that gives me a relation in terms of the parallel components of delta n and delta h. But I know what h is in terms of these normal components here. So I'm now looking at this second relation, just replacing for h. This second term here, n dot delta n, has a counterpart over here. So this term and this term cancel out. And then I've got, here I've got n squared, which is -1. And I've got a delta n with the index lowered, which I've also got on the right-hand side. So this tells me that delta n mu is a half n nu delta g mu nu. So it tells me that the variation of the normal is kind of related to a variation of the metric.
Sorry? Why do you raise the index on the H metric using the G metric? Like, on the second line on the right. Like, where did the G come from? It's like that.
Sorry, where?
So you've the relation H mu nu delta n mu is equal to n mu delta H G.
I'm sorry, which?
On this board, on the right-hand side, on the second line. No, the board's straight in front of me.
Which you mean the second line from the top?
Yeah.
Yeah. So, because H is just an element of the tangent bundle, so I'm just raising and lowering indices with G. I could raise and lower them with H as well, because once you've projected out the normal components, it doesn't really matter whether you raise or lower them with G or H, because the difference between G and H are just normals, and the normals annihilate H. So it actually doesn't matter in a sense. Sorry, there were so many H's on that board, I wasn't really sure which one it was. So, all this work here has just been to try and sort of figure out what the variation, what's going on with the variation of this normal surface in terms of looking at delta G and delta N. So now I want to think about what could I do if I wanted to add a term to cancel off that boundary variation. So let me just consider delta k, where k is the trace of the extrinsic curvature, which is also the divergence of the normal. So if I want to look at varying delta k, that's going to be a derivative of delta n plus the variation, the variation of the connection. So here, that's why I did all this work, to try and find out what delta n was in terms of delta g. So delta gamma is just given in terms of derivatives of delta g, and in this case, because you've traced over the upper and lower indices in the delta gamma, you just have a single derivative of delta g, and it's of the trace of delta g. And we've replaced delta n by n dotted with delta g mu nu. So you can start to see that this is beginning to look promising in terms of giving you something that looked like that boundary term from the Euler-Lagrange. So here, let me just do this differentiation. N nu grad mu delta g mu nu minus grad n of delta g. And then I've got to also take the derivative of n. So if I just move this board temporarily up a little bit, you can sort of see that here's the n grad g, which is this piece, and here is the normal derivative of delta g, which is that bit. So it's looking pretty good. And then, if I look at that final term here, so the covariant derivative of n is exactly k mu nu because of my coordinate choice. I've chosen n to be normal, to be unit, and geodesic, and therefore the derivative of n is exactly k mu nu, and also delta g mu nu is like delta h mu nu plus some normal terms, which will annihilate the derivative of n. So I can replace this last piece by delta h k mu nu. So this boundary term that we had, the Euler-Lagrange boundary term, so that's this thing lurking under here. So if I call this BT, so our boundary term, which was this piece here, I suppose I should put the minus 1 over 16 pi g, squeeze that in there. my boundary Euler-Lagrange term is now just the variation of the extrinsic curvature, and I've got a KAB term. And then finally, det H is equal to det G, at least because n squared is -1, again ignoring signs. And so this boundary term I have a feeling I may have a sign here, in which case, given the time, I'm just going to wrap up and we can sort it out offline. So what that means is I've re-expressed my boundary term as a variation of a boundary integral, and now something that is proportional to delta HAB. So this we're now happy about because it's just got delta HAB. It's no derivatives. And so this here, that is sitting in brackets with the 1 over 8 pi g, is the Gibbons-Hawking boundary term. So we add it to the Einstein-Hilbert action in order to make our Euler-Lagrange principle work. So,
But in the Euler-Lagrange formulation, what you set to 0 in the boundary is the variations of the 4 metric, right?
yes.
So,
Well, that's HAB.
so does that imply that you will have the variation on the boundary also equals to 0?
Yes, because delta HAB is going to be 0. So to just put it together, the full gravitational action is -1 over 16 pi g integral d4xr minus 1 over 8 pi g integral d3x root hk. So you're modifying your gravitational action, you're adding a boundary term, so that when you do the variation of this piece gives you the Einstein equations plus a derivative term. The variation of this piece gives you a derivative term cancelling that, plus this term here. And so normally with Euler-Lagrange, you say the variation of my field at the edges is 0, so that term would be 0. So that's from the perspective of bulk Euler-Lagrange. I kept that piece in because if you want to think about your boundary as actually being something physical and dynamical, you wouldn't necessarily set delta HAB to 0. You might want to also not just vary the metric inside, but vary the boundary itself, in which case that would also have to be 0. And that gives you some different sort of equations for the boundary in terms of the extrinsic curvature, which we will be looking at.
So that extra term now gives you non-trivial actions for Kerr and that you said at the beginning?
So yeah, so here we've got, when we do Euler-Lagrange, this gives us Einstein equations plus the boundary piece, boundary derivative piece. This cancels that, and it also gives this KAB minus KHAB term. And these are going to give us the Israel equations if we keep the boundary dynamical. But if we're just thinking about Euclidean actions or actions of different solutions, obviously we're not thinking about the boundaries being physical. It's just boom. It's something you put on as a sort of regulator. And so this term and this term together now both contribute to the action, because I guess, although we'll be doing it in full, if you think about, say, a black hole, where might you put a boundary? Oh, you put a boundary at large r. A boundary at large r is a sphere. A sphere has non-trivial geometry. It's got a non-trivial k, so we are going to pick up something that is non-zero. The question is, what is it, and is it regulated? And those are different issues.